All right, mon amis, it's time for us to do some problems involving l'hôpital. And the more we do, the better we're going to get. So make sure you do as many as you can. And it's important that you do these problems on your own as much as possible. So if you're watching the video, consider making frequent use of that pause button. And when you see a problem, try it out yourself first and see how far you can get. And then unpause and let's compare. And hopefully we get the same answer. And the more that you do, the more that you discover that you're able to do. So keep going. All right, well, let's begin. So our first problem, find the limit as x goes to 0 of x minus a half sine of 2x. Divide that by tangent of x minus x. All right, so whenever we're doing a l'hôpital problem, the first thing we do is say, all right, can we apply l'hôpital? So we ask ourselves the question, is it a fraction? And it is. And is it going to something indeterminate, 0 over 0 or infinity over infinity? So let's see what it's doing. So this is currently going to plug in 0, 0. That one's easy. That's 0. And then a half times sine of 0 is 0. Because sine of 0 is 0. Downstairs, tangent of 0 is 0. Minus 0. And we see, lo and behold, it is indeed 0 over 0. Which means that we're dealing with something which is indeterminate. Aha! That means we can apply l'hôpital. Wonderful! So we're going to apply l'hôpital. So I like to put a little indicator here that says, hey, I'm doing l'hôpital. The limit is still there because, hey, the limit hasn't been solved yet. That comes at the end. So now we take the derivatives. And remember, it's not the quotient rule. Derivative of the top, derivative of the bottom. So derivative of the top, well, derivative of x is 1. Then derivative of sine of 2x, well, derivative of sine is cosine. So it's still going to be a minus cosine 2x. And then we bring the 2 out by the chain rule, and 2 times a half is 1. So it's just 1 minus cosine 2x. Well, that's pretty nice. Downstairs, tangent of x, well, the derivative of that is secant squared. And the derivative of x is 1. Well, what does that do? Well, that goes to 1 minus cosine of 0 is 1. Downstairs, secant of 0 is 1. And then if you square 1, it's still 1. 1 minus 1 over 1 minus 1, which is 0 over 0. Okay, well, progress of a type. Certainly seems like it's getting a little bit easier. Still going to 0 over 0. And, well, let's keep going. So we apply l'hôpital again. And, of course, we can keep going. And hopefully, if we do it often enough, it'll turn out to be something nice. So we apply l'hôpital. Limit as x goes to 0. Derivative of 1, 0. Ah, beautiful. All right. Derivative of cosine is negative sign. There's already a negative, so that'll leave us with a positive sign. 2x. And by the chain rule, there'll be a 2 out in front. So positive 2 sine 2x. Downstairs. Derivative of secant squared. Well, derivative of secant squared, that would be 2 comes down. Then we have secant of x to the 1 times the derivative of secant, which is secant tangent. And the derivative of minus 1 is 0. All right. So that's it. Where is it going to? Well, upstairs, what do we have? We have 2 times sine of 0, which is 0. Downstairs, we have 2 times secant of 0, which is 1, times secant of 0, which is 1, times tangent of 0, which is 0. All right, so it's 0 over 0. Okay, good. So what can we do? Well, we can apply l'hôpital, right? Well, if we do that, maybe we should pause and say, hey, let's put the secants together. So 2 secant squared x tangent of x. All right, now we can proceed. So what do we have? Well, upstairs, the derivative 2 sine of 2x would be what? Well, that would be 2, and then derivative of sine is positive cosine, and then chain rule says there's another 2, so really it's 2 times 2. Downstairs, we have a 2. Now, secant squared x times tangent x. So the derivative of secant squared x, well, we took the derivative of secant squared x when we did that. So it'd be 2 secant squared x tangent x. That's the derivative of secant squared x times another tangent. Okay, so derivative of the first times the second plus the first, which is 2 secant squared x, times the derivative of the second, which is derivative of tangent is, again, secant squared. Now, what does this do? Now, the good news is we can see the the numerator, it's not going to 0 because cosine of 0 is 1. So whatever happens, it's going to happen right now. So what does happen right now? Well, what does happen is we see what? Well, we get 2 times cosine of 0. Well, cosine of 0 is 1, 4. Downstairs, 2 times secant of 0 is 1, and tangent of 0 is 0. So 2 times 1 times 0 times 0. So the first term is 0, plus 2 times 1 times 1. So 2, 4 halves, or 2. And there you go. Now, you may have done something slightly differently. One of the things that you can do is oftentimes say, hey, let me not always rush in and apply L'Hopital because things may start to get bigger and bigger and bigger. You start to notice things like this denominator is like, it's growing pretty big. Well, sometimes what you can do is you can say, well, I can do a little bit of manipulation, and that'll get me all the way that I need to get. So, for instance, let's come back up to here. So after we've applied L'Hopital our second time. So suppose we looked at this. You can say, aha, I can get rid of the 2's. You're probably thinking, that doesn't really do much. But wait, there's more. Okay, so suppose we had canceled our 2's. So I'm going to just put a little dot, 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 canceling my 2's. What else can we have done? Well, we could have also done the following. What's another way to write sine of 2x? Well, you can write sine of 2x as 2 sine of x cosine of x. That's the double angle formula. Now, what do we have downstairs? We have that secant squared. All right, that's 1 over cosine squared x. Then you have tangent. What's tangent? Tangent is sine over cosine. Do you see what you can do? You can cancel some signs. And see, the signs are what are causing the zeros. And now, if you say, hey, all these cosines downstairs, you can flip them up, bring them upstairs. You say, look, this is really the limit as x goes to 0 of 2. There's 1, 2, 3, 4 cosine, so cosine to the 4th x, and that's 2. And lo and behold, you're done. Now, what happened? Well, we saved ourselves an application of L'Hopital at the expense of a little bit of trig manipulation. Now, is this a good trade-off? And the answer is, it's not a bad trade-off. It's neither good nor bad. It's just a matter of what are you comfortable with. If you look at this and say, I am comfortable with manipulating terms and looking for cancellations, then this is a great thing to do. And if you look at this and say, probably don't do it. Do what you're comfortable with and gets you to an answer. Oftentimes, there's a simplification that might save you 1 or 2 steps in doing L'Hopital. And, 1 or 2 steps might not sound like a lot, but remember, every time we can simplify, we give ourselves a little bit better chance of not making a silly mistake. At least we have the right ideas, but silly mistakes, they're always hard to get rid of. But we do our best, right? We continue. Okay, let's do another problem. This one's actually important, so let's pay attention to this one. Of course, we pay attention to all of them, right? Find the limit as x goes to infinity of 1 plus t over x raised to the x power. Now, I haven't said anything about what t is, but right now, say t is any number. So pick a number from negative infinity to positive infinity. That's what t is. And the question is, what is this value? All right. Well, let's think about what's happening. So you have this 1 plus t over x. Now, t is a number divided by x, which is getting big. So I have a number over something big. It's going to 0. So this t over x is getting very small. So this is heading to what? Well, The 1 plus t over x goes to 1, and then, of course, the x goes to the infinity. So this looks like 1 to the infinity. Now, what do we know about 1 to the infinity? Well, the answer is we know that we get to do more work. More work. You see, 1 to the infinity is one of our indeterminate forms. It's something that by itself is not enough to determine what's going on. So how do we proceed? Well, we want to apply L'Hopital because that's what our new toy is, but also because L'Hopital is a fantastic way of figuring out what to do with indeterminates. But we can't do that until we have a fraction. So we're going to do something to make it into a fraction, and whenever we have exponents involved, so something to the something, the way we do that is we use logs. Okay, so here we go. Let's suppose for the moment we're going to say our limit of what we're looking for. We'll call it L. So L is the limit as x goes to infinity of 1 plus t over x to the x power. Now we take the log of everything, and we can say that the log of what we're looking for is, and because log is a nice function, we can push it in through the limit. So this is the limit of x going to infinity, the natural log of 1 plus t over x to the x. Now, properties of logs says that to the x power comes down. So, in fact, we're going to take it all the way down. See, normally we would say, aha, this x power that we see there, we would say, look, that is going to go all the way into the front, but then we're going to keep it traveling till it gets to the denominator. Now, if it came down and was an x in the front, by the time it gets into the denominator, what would it be? Well, it would be a 1 over x. So we have natural log of 1 plus t over x. Divide that by 1 over x. Okay, now we're ready. We're ready to take L'Hopital. Well, why? Well, let's see what's happening. What's happening upstairs, we have 1 plus a number over x, which is getting small. So really it's natural log of 1, which is 0. And 1 over a big number is getting small, so it's going to 0 over 0. So we apply L'Hopital. Ah, L'Hopital, mon ami. So this is our limit. X goes to infinity of what? Well, natural log, how do you take that derivative? 1 over the inside, 1 plus t over x, times the derivative of the inside. Well, what's the derivative of t over x? T is a constant, and we would say, look, it's really like x to negative 1. So I would have the t as the constant, and the derivative of 1 over x is minus 1 x to minus 2. Now, what's the derivative of 1 over x? Well, we just did it, right? This is really like x to the minus 1. So the derivative of that is minus 1 x to the minus 2. Or if you like, negative 1 over x squared, whatever you're comfortable with. Okay, so there's our L'Hopital. Now, some nice things happen. You can spot it, right? You see that negative 1 x to minus 2 is the same on the top and bottom. So what we really have is, look, we have this t. Now, t is a fixed value. It doesn't depend on our limit, so we can even pull it outside of our limit. So we have t, the limit, as x goes to infinity of 1 over 1 plus t over x. And the only place where x shows up is right there. And as x gets big, t over x gets small. So this part right here, that's going to go to 0. So I get 1 over 1 plus 0, which says the limit part is 1. And so we're left with t. All right, now remember, that's not our answer, because what is t? We follow our trail back. T is the log of our answer. Okay, so the log of our answer is t, and therefore we come to the conclusion that since the log of our answer is t, then our answer would be e to the t. And there you go. Like I said, this is going to be an important limit. Particularly, you're going to see this once you get into Calc 2 towards the end. So it's a good one to know because we'll see it again. All right, good times. Fun problem. All right, well, let's try another problem. Of course. All right. So, here we go. Find the limit as t goes to 0 of 1 over t sine of 3t minus 1 over 3t squared. Okay, well, what's happening? Well, what's happening is that when you plug in t equals 0, what do you have in the first term? Well, it's 1 over a very tiny number, which means essentially 1 over a very tiny number is a huge number. And same thing's happening here. 1 over a very tiny number is a huge number. So it looks like like an infinity minus infinity, which means it's indeterminate. We don't know what it is. But we're not giving up. It just means we need to do a little bit more work. More work, of course. Of course. So what do we do to get our more work? Well, we want to apply L'Hopital. Can we? Not yet. What do we need? Well, in order to apply L'Hopital, we have to have it in a form which has a fraction going on. See, right now it's a subtraction. We need to turn it into a fraction. So how do we get to a fraction? Well, we use some algebra. Algebra, isn't it great? I feel like calculus is a wonderful way to learn algebra because we're actually doing it. You know, in algebra we talk about the ideas. In calculus we do the ideas. And so it's a great way to learn. All right, so what do we have? Well, get a common denominator. I see that probably they both need a 3. They both need a t squared, and they both need a sine of 3t. So here, I'm missing 3t, right? Because I don't have the 3, and this is only a t, not a t squared. So I'll have a 3t. Now, on the other case, I've already got the t squared, and I got the 3. I'm just missing the sine of 3t. So sine of 3t. And all of that is divided by 3t squared sine of 3t. Good. All right. Now we've got ourselves a proper fraction. Does it go to something nice? Well, upstairs, 0 sine of 0 is 0. Downstairs, well, we have 0. Sine of 0 is 0. Very 0, extra 0-y. So yeah, lots of zeros here. All right, well, let's begin. So apply L'Hopital. So we apply L'Hopital, and we say this is the limit as t goes to 0 of, upstairs, take our derivative. Derivative of 3t is 3, minus derivative of sine of 3t. Well, that would be, derivative of sine is cosine. And then chain rule says bring a 3 out in front. Downstairs, product rule. So derivative of the first, 6t times the second, sine of 3t, plus the first, which is 3t squared, times derivative of the second. Well, derivative of sine is cosine of 3t times 3. All right, good. Well, what is this doing? Well, upstairs, what do we have? 3 minus 3, because cosine of 0 is 1, so it's 0. Downstairs, see, we have that t and that t squared. That's going to make both the terms 0, so it's still 0 over 0. All right, well, what do we do? Well, we do L'Hopital, of course. Aha, all right. Well, so let's do that. So L'Hopital, one more time. So this is our limit. T goes to 0. Derivative of 3 is 0. That's nice. Now, derivative of a cosine is a negative sign. It's already negative, so that'll turn into a positive sign. And 3t. Then the chain rule says multiply by 3. There's already a 3 there, so that gets us up to a 9. Okay, how about downstairs? What can we do? Well, let's work our way through it. We have the first term, product rule, derivative of 6t is 6 times derivative of, sorry, not times the derivative, just times the second. So derivative of the first times the second, plus the first, which is 6t, times the root of the second, which is cosine of 3t times 3. Plus, okay, root of the first, 6t times the second, cosine 3t times 3, plus, okay, then we have the first times root of the second. Now I'm going to put the 3t squared and the 3 together, so that's 9t squared. Root of cosine, well, it's negative sine of 3t, and then don't forget that there's a 3. Okay, good. There you go. Aha! Wow, good. Now, what's happening? Well, what's happening here is we see, hey, there's a sine of 3t. That means the top is going to 0. So that's going to 0. How about downstairs? Sine of 3t goes to 0, t goes to 0, t goes to 0, t squared goes to 0. All the individual terms are going to 0, and I'm up, you still go to 0. So it's going to 0 over 0. All right, good. Well, that means there's still more work to be done. Now at this point, you're probably like, that's a lot of work. Well, yeah, we got to be patient, right? And hopefully we'll be rewarded for our patience. I hope so. Hope so. And but notice that things have been simplified. See, like for example, the numerator is actually simpler than it was before. We've even gone down to a single term. Our denominator keeps getting bigger, but of course we could pause and simplify that by saying, hey, some of these things can go together. For example, here these two are actually the exact same thing. So what are they? Well, there's a 6 times a 3 is 18, t cosine 3t, but since there's two of them, that would really be 36 times t times cosine of 3t. And since we're in the mood to simplify, the end would be negative 9 times 3 is 27, t squared sine of 3t. All right, so we'll apply L'Hopital one more time. All right, well, let's see what happens. Okay, so here we go. Applying it one more time. We get the limit as t goes to 0. All right, here 9, derivative of sine is cosine, okay, of 3t. The 3 comes out. 9 times 3 is 27. Now, we're happy. Notice that our numerator doesn't go to 0 anymore, which means it's game over. This is it. Whatever happens is going to happen right now. Well, it's going to happen in a few minutes, because now we've got to work through the derivative of the denominator. Okay, so what is that? Well, 6, derivative of sine of 3t, well, would be cosine of 3t, but then I have to multiply by 3, so that 6 times 3 is 18. Now, come here. Then there's 36t cosine 3t, so the root of the first, well, that's 36 cosine of 3t, plus, then the root of the first, so root of the first times the second, 36 cosine of t, plus the first times root of the second. So 36t, then negative 3 sine of 3t. All right, then the end. Okay, root of the first minus 54t sine of 3t. And then, so root of the first times the second, and then minus 27t squared times the derivative of cosine 3t times 3, right? Derivative of sine is cosine 3t times 3 by the chain rule. Okay, which goes to what? Well, upstairs, cosine of 0 is 1, and we have 27. Downstairs, 18 times cosine of 0 is 18. 36 times cosine of 0, 36. Now, the t goes to 0, so that term's going to go away. This t goes to 0, that t squared goes to 0. 18 plus 36, also known as 54. So 27 54ths, known as 1/2. And that's it. That's the answer. Wow. Amazing. Amazing. We found it. And, well, just have to be patient, right? And, but, be careful. Be careful. Check your work. Check your work. All right. Good. Well, time for another problem. Of course. So here we go. Given that f of x is twice differentiable, f of 4 equals 6, f prime of 4 equals 1, and f double prime of 4 is negative 1, determine the following. The limit as x goes to 2 of x times f of x plus 2 minus 2f of x squared over x minus 2 quantity squared. All right, well, let's begin. So how do we begin? Well, we probably should say, what's happening? I mean, you always take a problem with the limit and say, plug in the limiting point. So in our case, plug in 2. So when we plug in 2, this is doing what? It's going to 2 times f of 4 minus 2 times f of 4 all over 0. Well, that's not so hard to figure out because the numerator is 0, the denominator is 0, it's going to 0 over 0, which means more work. It's indeterminate. We don't know yet. Not yet, but we will. All right, so what do? Well, we're going to apply L'Hopital. So apply L'Hopital, and what do we have? So this is our limit as x approaches 2, and so take the derivative of the top, product rule. Derivative of the first, 1 times the second, f of x plus 2, plus the first, which is x, times the derivative of the second, f prime of x plus 2. Then minus 2, here, use the chain rule, f prime of x squared times 2x. Now you might have said, wait, shouldn't have you used the chain rule on the x plus 2? I should have, and I did, I just didn't write it down. The derivative of x plus 2 with respect to x is 1. And all of that downstairs is the derivative of that, 2 times x minus 2 to the 1 times 1. Okay, so let's clean that up. So that's the limit as x approaches 2. And there's not really a lot to clean up here, but we'll just make it look a little bit nicer. F of x plus 2, x f prime of x plus 2, then minus 4x f prime of x squared. All of that divided by 2 times x minus 2. So what is that going to? Well, we plug in 2. So that's f of 4 plus 2 f prime of 4 minus 4 times 2 is 8 f prime of 4 all over 0. Well, I hope the top is 0. Otherwise, this is going to be a short problem. So f of 4 is 6. So we have what? This is 6. And f prime of 4 is 1. So 6 plus 2 minus 8 over 0, or 0 over 0. Which, of course, we know means more work. More work, of course. Great, fantastic. So let's do some more work. So what's our more work? Well, of course, we call out L'Hopital. Ah, L'Hopital. What a beautiful thing. So we apply L'Hopital once more. So L'Hopital. So what is that? Well, limit as x approaches 2. Take the derivative of the top. F prime of x plus 2. Product rule. The derivative first is 1. So it'll be 1 times f prime of x plus 2. Then plus the first, x, times the derivative of the second. Well, that'll be f double prime of x plus 2. And of course, chain rule says multiply by 1. Here, product rule. So derivative of the first, derivative of minus 4x would be minus 4 f prime of x squared. And then we have minus 4x f double prime of x squared, but times that by the derivative of the inside, which is 2x, and all of that. Derivative of 2 times x minus 2 will be 2. Good. And now we know it's over. We don't have to do any more L'Hopital because we can spot automatically the denominator isn't 0. So, woohoo! All right. It just really means that from now, we just got to plug in and see what happens. So we know we're going to get an answer because we have something all over 2. Okay, so what's over 2? So remember, f prime of 4 is 1. So we're going to have f prime of 4. 2 plus 2. So that's 1 plus f prime of 4. Okay, so that's another 1. Plus, okay, 2 times f double prime of 4. Well, f double prime of 4 is negative 1. So it's 2 times negative 1. Then minus 4 times f prime of 4. But of course, f prime of 4 is 1, so minus 4. Then minus 8. Okay, we're going to keep track of this one. Minus 8 times f double prime of 4, which is minus 1, times 2 times 2, which is 4. All right, there's a lot going on in this last piece here. So, some good news. 1 plus 1 minus 2. So those first three terms combine and cancel out. Boom, boom, boom. Good. And here, minus minus makes this become a plus. So I have 8 times 4, which is 32. So 32 subtract 14 gets us to 28 over 2, or 14. And there we are. So there's the answer. It's 14. Beautiful. Beautiful. All right, good. It's just a matter of being patient and checking. And, of course, whenever you're doing L'Hopital, always make sure you verify. Is it going to an indeterminate that you can use? Going to a fraction 0 over 0 or a fraction infinity over infinity? And if it's not, don't do the L'Hopital. You got to be more patient and keep waiting. All right. Well, let's do another problem. So, find the limit as x goes to 0, natural log of 1 minus x plus x squared over 2 all over x cubed. Now, kind of we can see, looking at this, that potentially we may have to take up to 3 derivatives. Because when you see that x cubed downstairs, it says, aha, after 3 derivatives, that x cubed will get to a constant. So, don't be surprised if we apply L'Hopital many times here. Now, I'm not saying that we will apply it 3 times. I'm just saying we might. We might. So, well, be patient. And here we go. So, first thing, well, let's find out if it even applies at all. Maybe we don't need to apply it. So, what happens when we plug in 0? So, log of 1 is 0 plus 0 plus 0 over 0. Oh, that is 0 over 0, which means, okay, so it is an indeterminate, which means we should definitely do some work. And here, our work is L'Hopital. All right, so we're going to do some L'Hopital. All right, so we apply L'Hopital, and we say, all right, this will be the limit as x goes to 0. Now, the derivative of natural log of 1 minus x, that is 1 over 1 minus x times minus 1. Where does the minus 1 come from? From the chain rule. So the derivative of natural log is 1 over the inside, but then you have to multiply by the derivative of the inside. In our case, derivative of 1 minus x is minus 1. Derivative of x is 1. And derivative of x squared over 2 is x. Downstairs, what do we have? Well, we have 3x squared. All right, good. That's what we have. Okay, now what? Well, here, what do we see? This goes to what? Well, we have minus 1 from the first piece, plus 1, and then plus 0, all over 0, which is 0 over 0. So, what can we do? Well, I think we know where we're going with this. We're going to try L'Hopital again. Okay, now, before we do L'Hopital, let's clean this up a little bit. One thing we can do is, you see this minus? We can take this minus and move it downstairs. So we can think of this as minus 1 plus x downstairs, or we can really think of this downstairs as x minus 1 to the minus 1 power. All right. Now, what happens? Well, what happens is that this becomes, if we do L'Hopital, this becomes our limit as x goes to 0 of minus 1, x minus 1 to the minus 2, and then derivative of plus 1 is 0, derivative of plus x is plus 1, all over 6x. Well, what does that do? Well, that goes to minus 1 plus 1 upstairs, and 0 downstairs, which is 0 over 0. And, okay, apply L'Hopital again. And what do you see? Limit as x goes to 0, minus 2 comes down. 2 times x minus 1 to the minus 3 plus 0, derivative of 1 is 0, over 6. And we're like, aha! Good. Whatever happens, happens now, because we're not having 0 downstairs. So, when you plug in 0, you get 2 times minus 1 to the minus 3. Well, that's going to be a negative 1. So you end up with a negative 2 upstairs and a 6 downstairs, or a negative 1/3. And there you go. All right, great, good, we got it, woohoo! Now, could you have done some other things? And the answer is, yeah, sure, why not? Let's try something. Let's, instead of jumping in and doing L'Hopital right away, let's come back here after our first piece. So notice everything here, it looks very much like algebra. It's just a rational function. So let's clean that up before we do anything with L'Hopital. So what would happen? Well, we have our limit as x goes to 0. And what do we have? Well, you have 1 over x minus 1 plus x plus 1, right? All over 3x squared. Now, if I wanted to combine these last two together, I need a common denominator. Well, this is really like x plus 1 over 1. So I'll multiply it by x minus 1 over x minus 1. Well, what does that become? It becomes a limit. X goes to 0. And here we're now having a common denominator of x minus 1. And here we have a 1 plus x plus 1 times x minus 1. It's a plus b, a minus b. That's x squared minus 1. All right. And then this 3x squared, I can bring it to the numerator, just put it down in the fraction. And now I say, but wait, it gets better. Because what do you see? The plus 1 minus 1 cancel. And then you say, but wait, it's even better still. The x squared and the x squared cancel. And what you end up with is you end up with what? Well, you end up with 1. Whoops, don't forget the limit. We haven't taken the limit yet. X goes to 0. 1 upstairs. And then downstairs, 3 times x minus 1. And now, we don't need to do any L'Hopital. Why? Because you just plug in 0. And what do you get? Upstairs you get 1. Downstairs you get 3 times negative 1. So you end up with negative 1/3. And you're done. So again, this is a case, we've seen one in other problems, where, hey, maybe if you just pause and say, let me clean up, do some algebra or do some trig identities, I may save myself having to do some L'Hopital applications. Which way is the right way? The answer is they're both correct. It's not that, this one's right and this one's wrong. It's just like, here's one way and here's another way. And you should do what you're comfortable with, as long as, of course, you get the right answer. That's the important part, is getting the right answer. All right. Well, let's do another problem. This one looks good. This one looks great. Find the limit, as t goes to 0, of sine of t over t, and all of that is to the power of 1 over t squared. Wow! That's crazy. See, we've talked about this limit before, sine t over t. Of course, now, with L'Hopital, that one's easy. But now we have this extra 1 over t squared floating around upstairs. So let's look forward to the fun. Okay, let's begin. So, what's happening? Well, what's happening here to the inside? What's happening to sine t over t as t goes to 0? Well, it's going to 1. That's something we know about sine t over t. Now, how about the exponent? 1 over t squared. Well, 1 over a small number becomes big. So it's heading towards infinity. 1 to the infinity, which means, of course, more work. Well, that's not surprising. We're kind of expecting there to be some more work involved. So now we have to figure out, okay, how do we go about doing the more work. Well, what we need to do is to find a way to get into a fraction. And whenever we have something both downstairs and upstairs, as we do here, the way we do that is logs. So let's suppose we say L is our answer. So it's our limit as t goes to 0 of sine of t over t to the 1 over t squared. All right, now we take our log. So the log of our answer, and again, log is continuous, so we can push it into the limit. So normally we would say it's the log of the limit, but that becomes the limit of the log, limit as t goes to 0, of log of sine of t over t to the 1 over t squared. This will, 1 over t squared, come all the way down. What do I mean by that? Well, really, this 1 over t squared comes down in front, but of course, it's already over t squared, right? So that says it really becomes the t squared in the denominator. So we now have that this is our limit as t goes to 0 of the natural log of sine of t over t all over t squared. Good. Now, what's happening? Well, sine t over t goes to 1, so log of 1 goes to 0. So the numerator goes to 0, and the denominator goes to 0, and therefore 0 over 0, we can apply L'Hopital. We've gone into the fractional form. Good, good. Now, before we take our derivative, let's pause and say, can we make it a little bit more pleasant to work with? And I suspect the answer is yes. Answers to those questions almost always tend to be yes. And in this case, we have log. Whenever you have a log, you can say, hey, logs have some beautiful properties. In particular, we see a log of something over something. So this is division. So division in logs becomes subtraction. So when I'm taking the derivative, I can think of it as log of sine of t minus log of t. All right? So that's going to be an easier thing to take a derivative of. Okay, so that's how we're going to think about our derivative. So let us proceed. So we're going to apply L'Hopital. So this becomes our limit as t goes to 0. Derivative of log of sine t. Well, the way you take the derivative of log is you take 1 over the inside, and the derivative of the inside goes upstairs, so that's cosine t. And derivative of log of t, well, the inside is t, derivative of the inside is 1. All right, and then downstairs we have t squared, derivative of t squared is 2t. All right, good. Progress. Well, progress of sorts, right? Okay, so now what? Well, we probably should simplify. Let's clean this up a little bit. Let's clean up our expression upstairs. So we're going to combine these two fractions together. So what is that going to be? That's the limit as t goes to 0. Common fraction will be, common denominator will be t times sine of t. So let's see, we'd have t times cosine of t minus sine of t divided by, then we have t sine of t. So that's the upstairs. Then the 2t will come up into the denominator, so I can write that as 2t squared. So 2t squared sine of t. Cool. Great. Good stuff. All right. Well, what do we do here? Well, let's see what's happening to it. So as we plug in t equals 0, we'll get 0, cosine of 0, 1, so 0. Sine of 0 is 0. Downstairs, lots of 0. Extra 0, in fact. So this is really going to 0 over 0. Okay, so let's do L'Hopital. All right, so we apply L'Hopital. All right, L'Hopital. Well, what is that going to tell us? All right, so we apply it, and we have this is the limit as t goes to 0. So here, we'll take the derivative of the top, product rule, derivative of the first, 1, times second cosine t is the root of the first times the second, plus the first times the root of the second. Well, the first is t, and the root of cosine is negative sine. And then, what? Well, minus the root of sine. Well, the root of sine is negative cosine. And then all of that divided by the root of the first, 4t times sine of t, and then plus the first times the root of the second. So plus 2t squared times cosine t. Now, what can we see? Well, let's simplify. Let's simplify. So, a couple of things. A cosine, good. Upstairs, gone. Wow, that's beautiful. Now, notice everything left has a t involved. So, let's cancel out the t's. Good. Also, great news for us. Okay, so what do we have left here? Well, we have limit as t goes to 0 of minus sine of t. Upstairs, downstairs we have 4 sine of t plus 2 cosine t. Whoops, I forgot there's still a t there. Times another t. There we go. All right. Haha. I just moved it. Good. I didn't forget. All right. So, there is our limit. Now, we just got to figure out, what's that doing? Okay. So, well, that's going to what? Upstairs, sine of 0, 0. Downstairs, sine of 0 is still 0. Cosine of 0 is 1, but then I'm multiplying it by 0. So, we get 0 plus 0. So, we end up with 0 over 0, which means, of course, more work. It's indeterminate. We don't know what it is. Not yet. But we will. We will. Okay. So, we're going to keep going. So, this is applying L'Hopital what? That's our limit. T goes to 0. Now, the root of minus sine is minus cosine. The root of 4 times sine is 4 times cosine. Then the root of the first, so that'll be minus 2 sine of t times t. And then, so the root of the first times the second plus the first, 2 cosine t, times the root of the second times 1. All right, good. Now, what is this doing? Well, the good news is the top isn't going to 0, which means whatever happens, it's going to happen right now. All right, so what does happen? Well, the top goes to negative 1. And the bottom, we get 4, because cosine of 0 is 1. Then minus 2 times sine of 0 times 0. Well, that's very zero-y. So minus 0. And then plus 2. Okay, so in other words, minus 1, 6. But remember, that's not our answer. If you follow your equal signs back, that's the log of our answer. So, the log of what we're after is negative 1, 6. So to get our final answer, which is our limit, so our limit as t goes to 0 of sine of t over t to the 1 over t squared, which is what we call the L, is e to the minus 1, 6. You might notice that oftentimes when we ever have some function to a function involved, our answer is often of the form e to something. And that's not a coincidence, because oftentimes the way we work with these problems is we start by taking the log. And at the end we have to undo the log, and we undo the log by using the exponential function. So maybe a little bit surprising, but maybe not so surprising after all. Okay, good. Good problem. Good problem. All right, well, let's do another problem. Okay, woo. So, our next problem. Find the limit as x goes to 0 of x times sine of 5x all over secant of 2x minus 1. All right, this one is kind of a nice cool down after the last one, right? So, let's see. First thing is, what happens at 0? We can see you have 0, sine of 0 is 0. And then here, secant of 0 is 1 minus 1, which is 0 over 0, which we know is code for more work. More work. It's an indeterminate form. So we're going to apply L'Hopital. So apply L'Hopital. We see this will be the limit as x goes to 0. So upstairs product rule. Derivative of the first, 1 times the second, sine of 5x. And plus the first, x times derivative of the second. Well, derivative of sine, cosine, and don't forget the chain rule, so there'll be a 5 that comes out in front. Downstairs, derivative of secant of 2x. Well, derivative of secant is secant tangent, so secant 2x, tangent 2x, and then we say, aha, chain rule says there should be a 2. And the derivative of minus 1 is 0. All right, we don't forget to check, right? Of course we don't forget to check, because we want to make sure we get the right answer. Okay, so what is this doing? Well, this goes to what? 0, sine of 0, then 0 times something is 0. Secant of 0 is 1, tangent of 0 is 0. So, still 0 over 0. So what do? Well, we apply L'Hopital. So, here we go. So, L'Hopital. This will be equal to the limit as x goes to 0. Okay, derivative of sine will be cosine 5x, and then there'll be a 5 in front. Now, here, derivative of x is 1, so then there's a 5 cosine of 5x. So, right, derivative of the first times the second plus the first times derivative of the second. So, that would be 5, derivative of cosine is a minus sine of 5x, and then times it by another 5 from the chain rule. And all of that is upstairs. Downstairs, okay, well, product rule again. So 2, derivative of secant is again secant tangent. And then, of course, there's another 2. So that's the derivative of the first times the second plus the first 2 secant of 2x times derivative of the second. Well, derivative of tangent is secant squared 2x, and then, of course, chain rule says put a 2. All right. Now, what does this go to? Well, hopefully it goes to something nice. We can sort of spot, do a quick sort of mental check upstairs. We see sine of 0 and the 0 says that term is going to go to 0. But cosine of 0 is 1, so you get a 5 and a 5. Those are both nice terms. They're great terms. We like these terms. So we say, okay, so hey, that just says the upstairs goes to something nice. So in particular, it's 5 plus 0. How about downstairs? Well, secant of 0 is 1, and tangent of 0 is 0. So the first term is going to go away because of the tangent of zeros. The last term, the secants of zeros are 1s, and then there's a 2 and a 2. So that's 0 plus 4. So you get 10 over 4, also known as 5 over 2. Good, good. You know, doing these problems is a lot of practice in our rules for differentiation, and also just being careful with simplifying. It's good to have practice. Great to practice. All right. Well, let's try another problem. Of course. So, evaluate the limit as x goes to 0 of 3 to the power x minus natural log of 3 times x minus 1. Divide that by 1 minus cosine x. All right. Well, interesting. Wonder what's going to happen here. So, first off, let's plug in 0. Well, if you plug in 0, you get 3 to the 0, which is 1. Then natural log of 3 times 0 is 0 minus 1. And downstairs, 1 minus cosine of 0 is 1. So you end up with 0 over 0. All right. Well, more work, which is fine. We don't mind. So now we say, all right, let's apply L'Hôpital. Okay, so here we go. L'Hôpital. Ah, mon ami. What a great thing. Limit as x goes to 0. And now we say, okay, to remember the derivative of 3 to the x. That one maybe isn't so tip of our fingers here. Let's just quickly, though, remember. How do we do that? So suppose you want to take the derivative of not 3 to the x, but let's just say any number raised to the power x. And one of the things you like to do is say, let's reduce it to something we've done before. So we say, look, I know how to take the derivative of e to the x. E to the x is great. Derivative of e to the x is e to the x. So we might say, well, how can I make a to the x look like e to the x? Can you? Well, yeah, you can. You just have to think about the rules. So it turns out, this is a nice fact, that if I have a number a, that's e to the log of a. So this is e to the log of a to the x. Or, properties of exponentials, this is the derivative of e to the log of a times x. We say, well, hey, e to something, that has a simple derivative. It's e to the log of a times x. So the derivative of e to the something is e to the something times the derivative of the inside. So that's what's upstairs. But of course, this inner piece here, this e to the log of a x, is the same thing as what we started with. So it's a to the x natural log of a. All right, so that was our quick reminder. All right, so now back into our regularly scheduled problem. So what's the derivative of 3 to the x? Well, it would be 3 to the x natural log of 3. And we say, that's probably why they have a natural log of 3 there. Why? Well, notice, what's the derivative of the next piece? Well, it's a constant times x. So it's just the constant, natural log of 3. And the derivative of minus 1, 0, gone. Downstairs, derivative of 1, 0, gone. Derivative of cosine is negative sine. There's already a negative. So that gets us to positive sine. So there we go. Now what's happening here? Well, when we plug in 0, 3 to 0 is 1. But then you have a log of 3 minus a log of 3. Downstairs, sine of 0 is 0. So we really get 0 over 0. Okay, good. So what do? Well, no surprise. Let's do L'Hôpital. More L'Hôpital. Ah, beautiful, beautiful. So L'Hôpital says this will be the limit as x goes to 0. 3 to the x, well, we did that already. It would be 3 to the x times log 3. There's already a log 3, so that gets us to log of 3 quantity squared. The derivative of log of 3 is 0. Not 1 over 3, 0, because log of 3 is a constant. So, all right, that part goes away. And then the derivative of sine is cosine. All right, so now, no problems when we plug in 0. So 3 to 0 is 1, cosine of 0 is 1, so we end up with the natural log of 3 quantity squared. And that's the answer. Ah, beautiful. Nice problem. Good stuff. Okay, well, let's try another problem. Okay. Next problem. Evaluate the limit as x goes to 0 of 1 plus arctangent of 3x, or all raised to the power of 1 over x. Now, you might think, you probably put this problem in because you love arctangent. Yeah, I do. It definitely was a deciding factor in when I threw this in, because it's just like, wow, anytime you can put an arctangent in, you really should. You really should. It's a fun function. All right, so let's think about it. Now, we can't apply L'Hôpital yet because it's not of the right form. What is it? Well, notice what's happening. When you plug in 0, you get arctangent of 0, which is 0. So this is going to 1, and 1 over 0, well, that's infinity. All right. So it's 1 to the infinity. Okay, so more work lies ahead. We need to get into the right kind of indeterminate form. So in other words, 1 to the infinity is not right. We need to turn it into fraction of a function over a function. Okay, so we use logs. So we'll say L, whatever we're looking for, that's what we're going to call our limit. Now, you might say, I'm not really comfortable with doing that. And let's come back to that in just a second. And I'll point out, if you're not comfortable, here's another thing you could do. But I think it makes it more cumbersome than just saying, call L what you're looking for. All right, so we say the natural log of L. And since we've done a few of these, I'm going to go ahead and trust that you can see what's going to happen. So we're going to take the natural log of this expression. The 1 over x will come down. So the natural log of 1 plus arctangent of 3x over x. Okay, so we took the log. We used the properties of logs to bring the exponent down. Life is getting pretty good for us. Now, what happens to this? Well, what does it go to? The upstairs goes to log of 1, which is 0. The downstairs goes to 0, right? Because x is going to 0, so x is going to 0. All right, so this is the right form. Two functions in a fraction going to 0 over 0. So we apply L'Hopital, and what does that say? That's the limit as x goes to 0. All right, so here we go. When I'm taking a log of something, it's 1 over the inside, so 1 over 1 plus arctangent of 3x, times the derivative of the inside, derivative of 1 is 0, plus the derivative of arctangent of 3x, 1 over 1 plus the inside squared, times the derivative of the inside, which is 3. Okay, so that's the derivative of log of 1 plus arctangent of 3x. All of that divided by the derivative of x, which is 1. Now, hopefully, this is reasonable to work with. So what do we see? Well, what's going to happen? Arctangent of 3x is going to go to 0. 3x is going to go to 0. So we have 1 over 1, which is good. So this is 1. That's 1. That's 0. This will be 0. So that's 1 over 1. So in fact, if you just sort of write it all out. So here we go. 1 over 1 plus 0 times 0 plus 1 over 1 plus 0 times 3 all over 1. We say, well, look, what don't you really need here? Well, you really don't need the 1 downstairs. That's not really doing anything. 1 over 1 is 0. You don't need the 0. You don't need the 1 over 1 plus 0. So the only thing you have is the 3. So that's what you have. So you have 3. Now, that's not our answer. Why not? Well, that's the log of our answer. So how do we finally get our answer? What we do is we use our exponential. So L will be E cubed. Okay, so there we go. That's the final answer. Now, I said before, maybe you don't like saying, well, let's call our answer something L and then do something to our answer. It's perfectly fine. Here's the other way you can do it. And you'll see we're absolutely justified in what we're doing, but it makes things kind of cumbersome. And so what else can we do? Well, we can say, hey, if we're taking our limit as x goes to 0 of 1 plus arctangent of 3x to the power of 1 over x, I say I really want a log. So what I'll do is I'll say, hey, this is the same as the limit as x goes to 0 of e to the log of 1 plus arctangent of x. So I see arctangent of 3x. I don't want to make that mistake. To the power of 1 over x. And now you say, hey, e, it's a nice function, so I can pass the limit inside. It's a continuous function. So this becomes e to the limit as x goes to 0 of the natural log of 1 plus arctangent 3x to the power of 1 over x. And hopefully I have enough parentheses there. And now this is a way to avoid having the L, but now it becomes a lot more cumbersome to write. So if you really are like, I just never give me an L. I don't want to ever have that. Then just go ahead and do it this way. But be warned, it's going to be a little bit more difficult to write things out. But maybe you like doing that, which is great. Wonderful. Okay, well, back to our regularly scheduled problems. All right, good. So, our next problem. Find values a and b so that the following function is continuous at x equals 0 and x equals 1. Okay, so there's our function. Wow, what a function. This is going to be interesting. Well, let's see what happens. Okay, so what do we do? Well, so what does it mean to be continuous? It means that there's no surprises. So what we want to have is that when I look at 0, the limit from both sides have to match up. You'll notice that from one side, it's pretty nice. From the other side, it could be better. So let's talk about 1. Maybe 1 is an easier one. So at 1, well, we need to have that the limit as x approaches 1 from below of g of x has to equal the limit as x approaches 1 from above of g of x. Well, when I'm coming from below, I look like ax plus b. So this is the limit as x approaches 1 from below of a times x plus b. And here, when I'm above 1, I look like this sort of unusual expression, but, it is what it is. So I can replace g of x by this rational function. The limit as x approaches 1 from above of x plus 3 quantity squared minus 16 all over x times x plus 4 minus 5. All right, well, this limit from below, easy. Plug in. You get a plus b. All right, well, what do you get over here? When you plug in, you get 1 plus 3 is 4. 4 squared is 16 minus 16, which is 0. 1 times 5 minus 5 is 0. Goes to 0 for 0. Now, what do? Well, actually, you can do two things. One thing you can do is say, hey, this is a rational function. I can expand, factor, I'll get some cancellation. Or you're like, you know what? I'm just all in for L'Hopital. I become a L'Hopital fanatic, and I'm going to go all the way. So we could go with L'Hopital. Both will give us the right answer. So we apply L'Hopital, and what do we get? Well, limit as x approaches 1 from above of, upstairs it would be 2 times x plus 3, and downstairs, product rule, the minus 16 goes away because it's constant, derivative of constant is 0. It would be product rule, derivative of x is 1 times x plus 4, then plus x times derivative of x plus 4, so that would be x, and then the 5 goes away. And we say, okay, well, what happens here? Well, it's more reasonable. So we'll get 2 times 1 plus 3, which is 8. And then downstairs, we're going to get, we're almost off the pace here. 1 plus 4 plus 1, right? So that would be 6. 8 over 6, also known as 4 thirds. 4 thirds. Okay, well, sure, that's it, right? Okay, so there we go. So what does that tell us? Well, it tells us that we have a relationship. A plus B has to equal 4 thirds. Now, that doesn't tell us what A or B is, but it tells us something about A and B if we put them together. Well, so what's the next thing we do? Well, the next thing we do is we say, aha, let's do 0. Same idea, right? So, well, same idea. Maybe a little bit more interesting work. So here we go. At 0. Same setup. So be continuous. We have to say the limit from both sides have to match. So the limit from below has to match the limit from above. Now the limit from above is pretty straightforward. That's the limit as x goes to 0 of ax plus b. So, and you plug that in, that's b. So we've got that all worked out. Now, the limit from below. Well, from below, that's what our function looks like. So this will be our limit as x approaches 0 from below of x squared plus 2 log cosine of x, divide that by x to the 4th. Now, what do? Well, what we do, no real big surprise here, is we think about, well, what's happening? When we plug in 0, well, 0 log of cosine of 0. Cosine of 0 is 1. Log of 1 is 0. So this is really going to 0 plus 0 over 0. So it's going to be a little bit of work. There's no fancy, hey, let's factor. No. These are not polynomials. So we're committed here. We're going to go quite a ways on this problem, I suspect. All right. So, well, let's begin. All right. So what do? We're going to apply L'Hopital. So here we go. Apply L'Hopital. It's going to 0 over 0. It's a nice differentiable function. Even though it's a one-sided limit, L'Hopital still applies. It doesn't matter one-sided, two-sided. You can still apply L'Hopital. So limit as x approaches 0 from below. So what do we have? We have 2x plus, here, what's going to happen? Well, 2, we have a cosine of x, and then we have a sine of x with a minus. Where is that coming from? So when you take a derivative of a log of something, it's 1 over to the something. So that's where the cosine of x is. And then the derivative of something, that goes upstairs. So that's where the minus sine of x is coming from. And all of that is over 4x quantity cubed. Okay, so good. Now, what happens next? Okay, well, let's see what this is doing. So this is going to say the following. This goes to upstairs, we have 0 plus 0, and downstairs we have 0, so 0 over 0. All right, well, more work, right? Absolutely, there's going to be more work involved. Now, it might help us to clean this up a little bit, so let's do that. L'Hopital, not L'Hopital, we're doing cleanup. Limit as x goes to 0 from below. We'll cancel off a 2, so we really have x, and sine over cosine is tangent. So x minus tangent of x, divide that by 2x cubed. So again, I canceled the 2 off of every term, and then sine over cosine is tangent. We still have the 0 over 0. All right, good. We need some more space. Let me go grab a piece of paper. All right, I grabbed my piece of paper here, and we'll move that up. Okay, so hopefully this is going to be enough space. So this is L'Hopital. We're going to say the limit as x goes to 0 from below of 1 minus secant squared x, because derivative of x is 1, derivative of tangent, secant squared, and all of that is over 6x squared. Okay, well, what does that go to? Well, secant of 0 is 1, so 1 minus 1 over 0, which is 0 over 0. Okay, aha! What does that mean? More work! Ah, wow. Okay, so this is L'Hopital. Limit as x goes to 0. Well, derivative of 1, 0. That's good news for us. How about the derivative of secant squared x? Well, think of it as secant x quantity squared. The 2 comes down. Secant of x to the 1 times derivative of secant, which is secant times tangent. And then that's all over 12x. All right. Well, can we do anything? Well, we can. In fact, if we want, we can almost stop here. we could do another L'Hopital, or we could say, hey, let's make some observations. So we'll do a make some observations type things. So notice that tangent. What can we say about tangent? That's really sine over cosine. And so what can you do? Well, you can do the following. The 2 goes into 12. So what do we have? This is limit as x goes to 0. 2 goes into 12, so that would leave us with a minus upstairs and a 6 downstairs. There's a secant, and this cosine, it's one over cosine, it's like another secant. So now we have 3 secants, secant cubed. All right, so that takes care of the secant, and that cosine. And then we have a sine x and an x. So sine x and an x. And now I say, hey, hold on. This sine x over x goes to 1. Aha, right? Right, it does. Let me, we're off the page again. That sine x over x goes to 1. Well, what does that say? Well, it tells us here that this piece, where does it go to? Well, secant of 0 is 1, so it goes to minus 1/6. So we have that the whole limit here is minus 1 over 6. Good. Now, working our way back, what is that? Well, so if you work it all the way back, we saw, lo and behold, this is, from our work on our other page, negative 1/6. And so that tells us that b here is negative 1/6. So b equals negative 1/6. Now, we're not done. We need to find a and b. But we just found what b is. So we know our answer will be a equals something, b is going to be negative 1 over 6. So how do we finish off? Well, we need to know what is a, but we come over here and say, since I know what b is, I can put it in. So a minus 1 over 6 is equal to 4/3. Well, 4/3 is another way of saying 8/6, right? Add a 6 to both sides, a equals 9 over 6, also known as 3 over 2. And so that's what a is, 3/2. And there we go. Wow, what a problem. This one took a little bit more work than normal. And we suspected we'd probably have to do a lot of applications of L'Hopital, because when you see that x to the 4th, it's like, I got to somehow knock that x to the 4th down enough so that I'm not getting a 0 downstairs. And oftentimes it's like, well, look, every time I apply L'Hopital, that knocks off one exponent. And the other thing is that at that last sort of part, we said, hey, we were able to get a sine x over x at the end to sort of help save ourselves one step. You could have kept going with L'Hopital, and you would have gotten the right answer. Of course, you just have to be patient. But isn't that true of a lot of stuff? As long as you're patient, things tend to work out. All right, well, progress. We're making good progress. Good. So, time for another problem. Okay, so what's our next problem? Find the limit as t goes to 0 of cosine of 4t plus 5t squared to the 1 over t squared. Another one of these problems. We've done a couple like these, so hopefully by now you got a little bit of the cadence. So we're just going to do this one just for practice, really, almost for fun. And hopefully by now we're getting the hang of these problems. So how do we do these? Well, initially we say, well, what's happening here? Cosine of 0, 1. 5 times 0 squared, 0. So it's really 1. 1 to the over 0. Well, that's like a huge number, so it's 1 to the infinity. Okay, so that's what's happening initially. And what is 1 to the infinity? Well, we don't know. It's indeterminate. So we've got to do some more work. And of course, our first step is we got to get to our fraction. So we'll get to our fraction using logs. So we're going to call this whole thing L. So the log of L is going to be the limit as t goes to 0. See, it's the log of this whole expression, but I'm going to push the log in to the limit of the log of cosine 4t plus 5t squared, and that's the power of 1 over t squared. And so we're going to bring the 1 over t squared down, and really it's going to end up with being t squared all the way in the denominator. So this is the limit as t goes to 0 of natural log of cosine 4t plus 5t squared. Divide that by t squared. So again, the 1 over t squared came down. Now, let's see where we're at. We do have a fraction. Let's make sure it's an indeterminate. So we're having cosine of 0, 1. 5 times 0 is 0. So this is log of 1, which is 0, over 0 squared, which is 0. Good, good. So we can apply L'Hopital. All right, ha ha ha. L'Hopital, mon ami. All right, good. So we apply L'Hopital, and what do we get? So this is, and just make a mark here what we're doing, limit t goes to 0. Now, when we're doing log of something, the way we take the derivative of log of something is it's 1 over the inside, so cosine 4t plus 5t squared times the derivative of the inside. Well, derivative of cosine is negative sine of 4t, and then here times the derivative of the inside, 4, and then plus derivative of 5t squared, 10t. So this 4 is coming from the chain rule. All right, so that's the derivative of the top. All of that divided by 2t. Good. Now, what do? Well, we have to clean up a little bit. Now, there's oftentimes you can say, well, let me see if I can sort of coax out a limit here, or say, well, let's keep going with L'Hopital. Both ways work, but I'm going to try to see if we can get a little bit of coaxing here, because what do I see? This cosine of 4t plus 5t squared, it's not going to be the funnest to work with, and it's not going to 0, so it's going to something semi-reasonable. The 2t, I say, well, the t and the t I could do something with, and I could probably get something going on here. So let's see what we can do. I don't know if this is going to work, but we'll try something. You know, that's oftentimes a great way to solve problems, is you try something. And if it doesn't work, try something else. But of course, the important thing, never give up. So, limit t goes to 0. This part, cosine 4t plus 5t squared, I'm just going to put in front because there's really nothing wrong with it. It's not going to make my limit have any issues. Okay, so that's that part. Then we have negative 4 sine of 4t, divide that by 2t, and then plus 10t divided by 2t. So what happened? Where did this come from? Well, I still had this 2t being divided, so I just take this 2t and divide it into each piece. Now, good news is at least one part is not so bad. You see this last part, 10t divided by 2t, it's really 5. You can get the t's to cancel, 10 over 2 is 5. This other part is really close to something. We always have in the back of our mind a really nice basic rule, which says that sine of blah over blah goes to 1 as the part on the inside goes to 0. So I'm just saying blah is a stand-in for something. It doesn't have to be sine theta over theta or sine x over x. It can be sine of something. So I look at this and say, it's so close. You see, it's 4t on the inside, but there's a 2t. They're not quite the same, but they're not so far off. So how do we do it? Well, we say, look, if I could just turn this 2 into a 4, that'd be great. So I can do that if I multiply by 2. If I multiply here by 2, I'm also going to multiply upstairs by 2. All right? So what happens? Well, now the sine of 4t over 4t, this piece, is really going to go to 1. So we're almost there. We're almost there. We put our pieces together. So what do we have? First off from here, cosine of 0 is still 1. 5 times 0 squared is still 0. So I have 1 over 1 plus 0. So this is going to go to 1. Then I have this is going to 1 times a negative 8. See, that's 4 times 2. So this whole thing here goes to negative 8. And this goes to 5. Negative 8 plus 5, well, is going to go to negative 3. So we have negative 3. That's our limit. So this is going to negative 3. Now remember, that's not our answer. It's the log of our answer. And therefore, we can say that our real limit we are after is e to that answer, negative 3, right? So get rid of the log, use the e, and there we go. That's it. Good. Good. We're getting the hang of these problems, I think. I hope so. I hope so. It's good to be able to do problems. It's oftentimes wonderful to be able to do problems. All right. Wow. Cool. Good times. Good times. All right. Well, let's do one more. One last problem. Okay, here we go. Find the limit as t goes to 1 of the natural log of 5 minus 4t plus e to the power of 2t minus 2 minus 1 all over 4 over pi arctangent 3t minus 2 minus 1. Okay, well, it looks a little bit intimidating. There's a couple of things. Oftentimes, our limits involve things going to 0, but they don't have to. This is a reminder. Look, things can go to things other than 0. So that's good to keep in mind. And this is also a nice sort of mixture of functions. Well, let's begin. First off, what's happening? We check and say what happens when we plug in 1. So 5 minus 4 makes natural log of 1, which is 0. Then we get e to the 2t minus 2, that's e to the 0, which is 1. And then we're going to subtract 1. Downstairs, we have 4 over pi, and then we have arctangent of 3 minus 2. Well, that's arctangent of 1. Do you remember arctangent of 1? It's pi over 4. All right, remember? So when we talk about arctangent of 1, what does that really mean? Well, arctangent of 1 is something, and that's really the same as saying, well, look, I'm looking for an angle, something angle, and when I take the tangent of that angle, it gives me 1. And so it's a 45-degree triangle, but of course we're in calculus, so we don't say 45 degrees, we say pi fourths radians. And let's see, and then minus t, so that's minus 1. And 1 minus 1 is 0. Here, 4 over pi times pi over 4, that's 1. Minus 1 is 0, so it's 0 over 0, which means more work, more work. We got to apply L'Hopital. Okay, so here we go. We're going to apply L'Hopital and see what we get. So go through it term by term. Derivative of natural log of 5 minus 4t. Well, what will that be? It's going to be 1 over 5 minus 4t. And then in the numerator, we take the derivative of 5 minus 4t, which is negative 4. Then derivative of e to the 2t minus 2, well, it's e to the 2t minus 2, because e to anything, the derivative of that is e to that anything, times the derivative of that anything. So we're doing the chain rule. So really, these are the chain rules that we're talking about here. That's where the negative 4 came from. It's also where the 2 came from. Derivative of minus 1, 0. Gone. All right. Then we have 4 over pi. It's a constant. Derivative of arctangent, 1 over 1 plus the inside squared times the derivative of the inside. Well, the derivative of 3t minus 2 is 3. And then the derivative of minus t is minus 1. All right, good. So we took our derivatives, and there we go. Now, what do we do? Well, let's plug in 1, and maybe we'll get a number. And if we do, we're done. Okay, so when we plug in 1, we have 5 minus 4 is 1, so we get negative 4. That looks pretty promising. So let's see, negative 4. Then we're going to get e to the 0 again, which is 1 times 2. So negative 4 plus 2. So now, definitely, we're done. Whatever happens, happens right now, because we're not 0. Okay, how about the downstairs? Well, 4 over pi. And then what do we have? We have 3 minus 2 is 1, right? Yeah, it is. So squared is 1. So 1 over 1 plus 1 is a half. And then we have times 3. All right, times 3. And then minus 1. All right, so that is our answer. Oh, but let's clean it up. Let's make it look nice. Isn't it great to make things look nice? Negative 4 plus 2 would make negative 2. Downstairs, we're going to get the 2 to go into the 4. So that would be 6 over pi minus 1. And from here, let's multiply everything by pi. So we end up with not a fraction, but a fraction, right? So we're multiplying top by pi and the bottom by pi. So we end up with minus 2 pi. Divide that by 6 minus pi. And there you go. All right. Well, maybe not exactly what you would have thought when you started, but not so bad. You do the work, and you find the answer. And that's oftentimes what happens when you're doing the problems with L'Hopital. All right. Well, that is a lot of L'Hopital practice. So by now, hopefully we feel like we're L'Hopital fanatics. We're experts. And I hope you got enough. And, of course, there's always more, right? There's always more problems. So keep going. You're doing great.